Welcome back. In this video, we'll be talking about Numpy and Matplotlib, two libraries that we'll be using frequently as we develop artificial intelligence solutions. Numpy is a library designed for operating on high-dimensional arrays, or tensors. It's designed to do basic arithmetic on tensors very quickly. In fact, it executes much faster than handcrafted Python code. It's convenient. Its syntax allows us to efficiently express operations on tensors. And one of the features that contributes to both of these is that Numpy does implicit iteration. If we have two high-dimensional tensors and we wanted to add them together element-wise, one way of doing this is to write a set of nested Python for loops that iterate across all of the possible indices and add together the appropriate elements. In Numpy, all we have to say is that we want to add the two tensors together, and it takes care of all of that iteration structure for us. This makes it much easier to write correct Numpy code and to debug it if it was incorrect. Some operations in Numpy are more than 3,000% faster than doing the equivalent operation in Python. Even things as simple as applying a map operator to apply a function to each element in an array. As a simple example, Fibonacci numbers can be computed using repeated matrix exponentiation. Multiplying matrices together is something that Numpy supports. So if we write some handcrafted Python code to multiply matrices together as efficiently as possible and compute Fibonacci numbers, it might be more than 30 lines of code. And in fact, we can do the same thing in Numpy using a single line of code. In fact, the Numpy solution is way faster. So Fibonacci numbers probably aren't that interesting to your business, but even something as simple as multiplying matrices together, you should use Numpy for it and not write your own thing in Python. Matplotlib is a library for plotting data along two axes. We'll use it to plot our input data. We'll use it to plot predictions or regressions. We'll use it to track the performance of algorithms or models over time, or as we change parameters of those models or make them more complex. This will be really useful for understanding how well we're doing, and also for understanding why things are working the way they are. This will be helpful for debugging. So let's try some things out in Numpy. First, we'll import the library. Now, Numpy requires us to create a Numpy array. One way of doing this is by passing an iterable collection to the array command, which will create a Numpy array. Every Numpy array has a shape. This will tell us how many dimensions there are, and also how large the tensor or array is along each dimension. In this case, we have a one-dimensional array that has 4 elements. We can also generate arrays using the command arange. This is comparable to the range command in regular Python. I note that this is arange. There's only one R. That stands for array range, not for arrange as like organize. What arange does is create a one-dimensional tensor with values going from 0 up to 1 less than the parameter that you passed. If we want to change the structure of the matrix, we can use the reshape command. We can pass in a new set of dimensions. Now the size of the tensor, the total number of elements, can't change. But we can use this to change the number of, say, rows or columns that our array has, or to turn it into a 3-dimensional or a 5-dimensional tensor. In this case, we'll reshape one-dimensional 20-element tensor into a 2-dimensional 20-element tensor with 4 rows and 5 columns. Note that by convention, rows comes before columns. We can also create an array of all zeros. And to show off some of the power of Numpy, we can do scalar operations element-wise, just using the simple plus or times syntax. So if we wanted to add 0.5 to each element in the array, we can just use this plus 0.5 syntax. Or if we want to double the value of each element in the array, we can just multiply it by 2. So you can see this gives us an array full of 0.5s and then an array full of 1s. Now there's an easier way to get an array full of 1s, which is to use the ones command. Again, we pass in the dimensions that we want and it returns a tensor where each element is 1. If you're interested in creating matrices to multiply by, you can use the identity command. This will create a square identity matrix. Now, one of the nice features of Numpy is that we can index into a particular element in the tensor using this indexing notation. We can give the index of the row and then the index of the column separated by a comma, and then we can assign a value to that element. And this will change the value in place in the tensor. So here we see that this element has changed to 42. Now Numpy has some other nice indexing functionality called slicing that will allow us to take contiguous blocks of data from our tensor. We'll explore that a little bit in this example where we load in a dataset and do some processing on it. So first we're going to load the datasets module from sklearn. It stands for scikit-learn. And then we'll load pyplot from matplotlib. This will allow us to generate graphics. This may take a moment to load. Once it does, we'll be loading the iris dataset from scikit-learn. The iris dataset is a collection of 4 measurements of a variety of different flowers. There are 3 species of irises that are all related, and these are physical measurements of those flowers. The iris dataset is somewhat famous and also fairly small, which is why we're using it. Here you can see that there are 150 rows and 4 columns in this dataset. So there are 150 instances of a flower, and there are 4 measurements for each flower. You'll also see that we have a set of labels. These tell us what species of flower it is. As I said, there's 3 different types. And the labels are a one-dimensional 150 element list. Now let's say that we wanted to select only the middle 50 of the data points. We can do this using the slicing notation that I mentioned earlier. What we can do is say start at element 50, or the 50th row, and go up to but not including element 100, or the 100th row. We use the colon to say take everything in between. We can use slicing along multiple dimensions at the same time, so we could also say, instead of taking all of the columns, let's only take the last 2 columns. If you remember, there are 4 columns, and they're indexed 0, 1, 2, 3. What we're saying here is start with column 2 and go until the end. Leaving it blank means go to the end, and if you leave it blank before the colon, it says start from the beginning. If we look at the shape of the data we've just sliced out, we've picked out 50 rows, each of which has 2 columns. Now let's scatter plot this data. We'll use the scatter command, and the first argument will be the set of x values, the second argument will be the set of y values, and here I've included an optional argument that specifies the color. It happens in the iris dataset that the first 50 are all one flower, the second 50 are all another flower, and the third 50 are all a third flower. So these will all have the same label and therefore the same color. You can see here that we're using the slicing notation again. The colon with blanks before and after says start from the beginning and go to the end, and we'll take the 0th column, that is the first column of data. And then for the y data, we'll take all of the rows, but we'll take the second column. We then use the show command to show all of the scatters that we've done since the last show command. And this is our data set. Let's load a slightly different data set that's called the moons data set for a reason that will become apparent in a moment. These are some parameters that affect the generation of the moon's data. It's randomly generated. And I'm going to print out the labels of the first 10 elements. We'll scatter them and then show them. As you can see, the labels are all mixed together. So different rows may belong to one set or another set. And here there are two sets. There's the purple set and the yellow set. So all of the zeros, for example, might be this purple set, and all of the ones might be the points in this yellow set. Let's see if we can get just one of these moons by themselves. If we want to get just the rows that correspond to having a particular label, that is, they belong to, say, the purple set, we might want to combine the data for the labels and the location of the point. We'll use this append command to combine two matrices along a given dimension. If we try this, we'll see that we get an error. It says that all the input arrays must have the same number of dimensions. At first, this might be confusing because we have a matching number of rows. It seems like we should be able to kind of combine them nicely. But the problem is that the first thing, the moon's data, is a two-dimensional array, and the second thing, the list of labels, is a one-dimensional array. Even though they have the same length, they are not the same array data type. So what we'll need to do is use the Reshape command to change the labels from a one-dimensional array to a two-dimensional array that only has one column. If we do this, we can append the data appropriately. So now the first two columns are the original data, and the third column is the label. Now we're going to see something that is really cool and really powerful. Numpy allows us to select data from a large data set using conditions. This is a little bit like the functional programming that we saw in the previous video, but on a low level, it's slightly different. This slice here is taking the last column, that is the column with index 2 of our data plus labels. So in this case, just the labels. And then Numpy knows that whenever we have this kind of comparison operator, say equals 0, we really mean do an element-wise test of whether or not this is equal. So this total expression is now an array that has zeros and ones, or falses and trues, indicating whether or not the condition was true. We can now use a special kind of indexing where we pass in this array that happens to have the right length and take only the elements in the data set where the condition was true. That is where the label was 0. If we look and plot only the points that were selected by that filter, we'll see that we have selected the purple moon. As a quick aside, if you go on the repository for this course online, you'll be able to explore this code in more detail. I've left some extra things. For example, the code that was used to generate the experiment whose plot you saw in the slides earlier. I've also left some extra notes about using notebooks effectively.